Welcome everybody again to one of these Thursdays NanoSpin-off talk. So we have already have many of these talks. The idea is to disseminate what the startups, spin-offs at different stages of their business, how they are developing the nanotechnologies that are taking part of our daily lives more and more. So today, I'm glad to present Ines Black from the company CRAMIK Print3D. CRAMIK Print3D. Ines, she is a chemist. After she graduated in chemistry, she had 2 masters, not only one, 2 masters, both, let's say, more related to the field of health and molecular science and health. And then she started joining different companies as technician, and also the company Plus, which is more a research and technological center, let's say. And there she found that working on nanotechnology was really excited. And then the next step was moving to this company that she's going to present today, CRAMIK 3D printing. And she is research and development manager. So she knows everything about the business, what's going on in the company, where to go, the different applications that they are working. Today she's going to present the business and also the one example of an application related to these ceramics. And of course, all the questions that you have. So the floor is yours, Ines.
Thank you. Hello, my name is Ines Blanc. I am the R&D manager in CRAMIK, that is the company that I'm going to introduce you in a few moments. CRAMIK is a spin-off from the University of Castilla-La Mancha, specifically from Albacete, like me, I'm from Albacete too. As Reyes said, I studied chemist degree in the University of Valencia and a biochemist master in Valencia. And I'm going to tell you the history of the company and how we introduced engineering ceramic or tech ceramics in the additive manufacturing market or environment. I assume that additive manufacturing, this concept is more popular, and I thought that engineering ceramic too for him, for example. But when I talk about engineering ceramics, people think in traditional ceramic like pottery, crockery, or something else. But this kind of traditional ceramic has nothing to do with tech ceramics. That is our expertise. So I divided the presentation in 5 main points. The first 4 is about the company, who is CRAMIK, why tech ceramic, why additive manufacturing, and some concepts about business and startups. And the last point is a case study which I had to face when I arrived at the company. And the concept was the solid-state batteries manufacturing by FDA. So, who we are? CRAMIK is a material tech startup specifically focused in engineering ceramics. Okay, this kind of materials presents many interesting properties. For example, high temperature resistance, mechanical strength, stability, lightness. This is important property because many industries nowadays want to change metallic parts for thermic parts to reduce the weight. And moreover, we can introduce additives to tailor our ceramics with new properties. For example, semiconductive behavior, ceramic electrodes. This is the This is the goal in our case study. We print the electrodes and we produce a put cell prototype. But then and we can control the porosity in the ceramic part. With this kind of properties that this tech ceramic present, allow us to take a place in a high-tech market. For example, aerospace industry, automotive, medical, or energy and telecom industries. In this slide, I want to show you some examples where we can find tech ceramic in the real life. Okay. For example, in aircraft, we can find tech ceramics in engines and in brakes. In aerospace vehicles, like insulating tiles, nose cones, and high temperature coatings. In automotive industry, for example, we can find tech ceramics like engine parts, and in the medical industry, like implants. It's more popular. And in the energy and telecom industry, like ceramic solid-state batteries, this is the example of our case study, the bootstrap prototype. And in antennas, like dielectric materials. So, related to this kind of properties and our target markets, CRAMIK has developed a material portfolio. Divided in different categories, depends on the application. Okay, for example, thermal materials for application which need temperature environments more than, for example, 1500 degrees. Clay materials for bead geometry with high material deposition rate. This kind of materials is more similar than traditional ceramics, for example. Biomaterials for complex geometries in touch with epidermis and the pharma industry. And electromaterials for energy and electronics application with the design freedom is the key. In this slide, I want to show you our material portfolio. Okay. For example, in electro, LTO and LCO was the materials that we chose to print the electrodes. Okay. LTO like anode and LCO like cathode. And zirconia with lithium is the material, the dielectric material in antennas, for example. Okay. Like I said before, CRAMIK is a spin-off. Okay, and we were born from an idea, and this idea was produce ceramic filaments for fused deposition modeling. Okay, one of the 3D printing techniques. Now we have created a 360 service where we offer a 3D design consultancy, manufacture ceramic based material ad hoc, okay, and the possibility to manufacture or produce the first samples in small batches or for prototyping, to help our client to apply our innovative technology in their industries. So I was speaking about the material, but I don't tell you how is our material and how we produce it. Our material, we produce 3 different formats: ceramic slurry, ceramic pellet, and filament. We always start from an initial product that is the ceramic slurry, and then we can produce pellet or filament. All of them are based on the same formulation. An inorganic part that is the commercial ceramic powder, whatever, and organic part that is our expertise, because it's a thermoplastic blend we call binder, and is patented by CRAMIK. and allow us to introduce, in general, whatever kind of ceramic powder. Okay, and the format depends on the technology where you want to apply it. Now you already know how is our material, and now I want to explain you the whole process. Since we produce our material until we obtain a full ceramic part. Okay. When we produce our material, first we use software design to design the part, the need of the client. We use the second step is use our product to print this part, and in this step we have the first part, and we call green body. Okay, in this part we still have organic part and inorganic part, but like I said before, we only want the inorganic part. Okay, so we have to remove the organic part. For this reason, we introduce the green body in a high thermal furnaces to first degrade the organic, and for this reason, this part has this color, brown body. Okay, here the organic is degraded, and then the second part of the thermal treatment is remove all the organic part. Okay, and we obtain the full ceramic part that is the center body. Okay, we can see a shrinkage effect, and it's a very important factor because we have in the first step oversize the part. Okay, so this is the whole process. Now you already know why we chose tech ceramics, and now I'm going to tell you why we chose additive manufacturing technologies. In this slide, I show you, I think, the most important technologies in the additive manufacturing market. First, fuse deposition modeling is one of the technologies which CRAMIK is specifically focused. In this kind of technology, we can use filament and pellet, two formats, and we only use the material that we need. In SLA, you have a photocurable binder, and you cure with a UV laser, layer by layer, until the product is complete. And in SLAs, you have powder bed and sinter layer by layer with a high temperature laser until the product is complete. So here I show you a short comparison between traditional manufacturing processes versus additive manufacturing processes. Traditional manufacturing processes are a kind of subtractive manufacturing processes and present some advantages such as cheaper mass production and global availability. Some examples: CNC machining, forming, joining. Related to additive manufacturing processes, the production time is lower than additive manufacturing processes. These processes require expensive tools to make parts. These tools suppose a lead time, and this lead time can mean a delay. Okay, so 3D printing technologies change this dynamic because remove this tooling stage, allow us start the production after the design. And this means a faster time to market and a competitive advantage. The production cost is lower than traditional manufacturing because only you only you use the material that you need. And this concept is in relation with the sustainability. 3D printing technologies are effectiveness because allow us the possibility to do an unlimited iteration or modification in the product file or in the CAD, okay, without extra cost in the software. Complexity maybe is the most popular advantage in 3D printing technologies. This kind of technology brings us freedom to design. Whatever you have in mind, you can produce. The development speed is faster than traditional manufacturing because the time from the idea to the final part is faster. Okay, is reduced. Moreover, we can save money in warehousing because this kind of technology works on demand. And finally, this kind of technology brings us millions of possibilities. And nowadays, many industries are adopting this kind of technology in their industries. Okay, now you know why I chose additive manufacturing technologies. And at the same time that we develop the material and we search the technology where apply our material, we needed some information about the present and the future market of the tech ceramics in the additive manufacturing environment. For this reason, we use SmartTech, that is a provider of market research and industry analysis in the additive manufacturing sector. And we could see that the growth of the ceramic materials in the additive manufacturing market was exponential. It's exponential. Okay, it's a good news for us because it means well, give us time to be ready to the turning point that will be in 2025. If we pay attention only to tech materials, tech ceramics, okay, here we can see that the growth is the same, is an exponential growth. And the market is divided in three different trends: hardware, tech materials, and tech application. Hardware is all related to 3D printing machines. Tech materials is a product, is a family where belong our tech ceramics. And tech application, maybe here we can find software that is an important tool because give us the possibility to predict the behavior of our material in the machines or in the thermal treatments, for example, and save money and time. With all of this information, we realized that we needed strategical partners in the software and hardware fields. Okay, and for this reason, we decided that our business model is a B2B. Okay, B2B is mean business to business. There are many different business models, but we thought that B2B for us is a win-win. Okay, for example, if we supply our product to hardware or software clients or companies, we can achieve information about the behavior of our material, and they achieve a new material in their portfolio, for example. So in this slide, I want to show you the whole ecosystem in the additive manufacturing market. you can see the whole techniques in additive manufacturing depends on the format, and we can see that the most of the companies are in the filament and liquid format, and this kind of information give us this kind of picture or diagram give us information about the market and what maybe is our target market. Okay. Okay, to finish the business part, here I show you the stage of the startups. Like I said before, CRAMIK is a spin-off and was born from an idea that was which was produce ceramic filament for FDM technologies. One format for only one technique. Okay. In this moment, we was in pre-seed stage, and now we are in early stage, maybe in Syria. We are working in a pilot plant to produce a quantity of batches of amounts, and to advance or to pass to the next stages, we had to do two things, or we needed two things: money, always money, and we searched financial sources, investments, grants, important, and we need change our mindset, okay? Because we were born from only one format to only one technology, but now our mission is the 360 service, okay? 3 formats for many different technologies. So the message here is, if you are thinking in build a startup or something like that, don't be afraid about change your mind, because we have to change to be a place in the market. That is the most important thing. Be a place in the market. This is the most important, because if you don't have place in the market, you don't have any. Sorry. And here I introduce you the CRAMIK team. We are 6 people, and in a few days, 7. So it's a pleasure work with them. And if you want, you can visit in Valencia. You visit us. Okay, this is the case study. Okay, this case study is consists of producing solid state put cell prototype. Okay, is the result of a research supported by a Spanish science grant. And the goal was analyze if the fused deposition modeling technology was suitable for the battery fields. Okay, so in this case study, we carry out the whole process, the whole productive process. Okay, we produce the ceramic filaments, LTO and LCO for anode and cathode, then print the electrodes, remove the organics to obtain a full ceramic electrode, okay, without organics. And we use this reactive like electrolyte. And we study the physical and the electrochemical properties of our full ceramic electrode to ceramic electrodes manufactured by casting Dr. Blake. Is the most common procedure to obtain battery electrodes. Okay. In this technology, you have a slurry tube and introduce the active material, but in this case, spread the slurry to obtain a thin layer. And this is the electrode, and here there is a organic part too. Okay, in our case, no, only full ceramic part. So we studied many materials, and finally we chose LCO and LTO to carry out the case study. Here you can see our printed electrodes and the casting electrodes. The first difference is our LTO is white and casting is black. If you do in casting technology, introduce additives to improve carbon black, for example, to improve the electrochemical properties. In our case, the electrode was full ceramic, so I think it's not necessary. Here you can see the techniques which we used to carry out the case study. First, physical characterization and the electrochemical characterization. Okay, the physical characterization. We carry out X-ray diffraction studies to check that the crystalline structure in the full ceramic electrode after the whole productive process was the same that the raw material, the powder, okay? And the results show that the structure crystalline was cubic and it's the same, okay? The same study was carried out with LCO, okay? In this case, the crystalline structure was trigonal. We did same to study the surface of the electrodes, okay? And with this study, we realized that if we increased the temperature, we achieved more densification in the electrodes, okay? The difference, increase the temperature with the same at the same time, and more or less the same effect we can see if we apply the same temperature but we increase the time. We carry out porosity studies to analyze the porosity, because it's important for the electrochemical studies to analyze the active surface. Okay, and we can see that LTO present a homogeneous distribution, homogeneous porosity distribution, and in LTO is heterogeneous because we have this area and more size. Okay. This is, I think, due to for the nature of the raw material. Okay. And to finish the physical characterization, we carry out TGA studies to check that the thermal treatment was fine. Okay, the all organics was removed, and the results shows that the weight loss is not representative, so was fine. Here in this slide, you can see the assembly procedure. Okay, here our printed electrodes, and we study the electrochemical the behavior or properties first of each electrode separate. Okay, first LTO and then LCO, and then at the finish of the presentation, the electrochemical behavior of the put cell. Okay, together. LTO and LCO, but first each electrode. So we carry out electrochemical impedance spectroscopy. This kind of technique shows us the resistance of the electrode to three phenomena. The resistance of the electrode to the electrolyte, to the charge transfer of the reaction, this R, and to the diffusion resistance. This diagram is called Nyquist plot, and I show you because in the next slide we are going to see more. This is the typical Nyquist plot. Okay, in our case study, we compare the Nyquist plot of the casting electrodes here, LTO and LCO, anode and cathode, to our printed electrodes. Okay, and we can see that in the case of LTO, the specific resistance is lower than casting LTO, so well. And in the case of LCO, we can see that this value is higher than LCO casting. So this kind of diagram give us information about the stability of the electrons. We can see that LTO is more stable than LCO. Okay. We carry out cyclic voltammetry studies to check that the basic electrochemical values in our print electrodes was similar to the reference values in the literature. Okay, and we obtain good results better than the casting technique. Okay. And we carry out capacitance and cyclability studies to check or to study the performance and the stability of the electrode. During 3 cycles at certain rate, we compare casting electrode than printed electrodes. Okay, anode LTO. And we can see that the capacitance values in the printed LTO was higher than casting LTO, and the effectiveness is better. Okay. The same for LCO electrodes. In this case, our printed LCO is not stable. Okay. The same study during 3 cycles, and we changed the rate. First C5 and C. And we can see that capacitance values decrease when the rate is increased. Okay. This is the C5 region, and this is the C region. And we increase the cycles in a rate C5, and we can see that when the cycles are increased at the same rate, the effectiveness and the stability of 3D printing electrons is improved. To finish the electrochemical studies for the electron, each electron, we studied the surface capacity, and we can see that the values for print electrodes are higher than casting electrodes, and it's due to because our electrodes are full ceramic, and in casting they still have organic part. And there are our food cell prototypes. Okay, here inside we have our LTO and LCO printed electrodes, and with electrolyte liquid. And this is the machine we have. And we studied the electrochemical properties too with spectroscopy. Okay. In this Nyquist plot, we only can see the slash related to the diffusion resistance. We cannot see the R. So give us information about the stability. And we carry out loading and unloading diagrams to check the performance and the stability. The sample ones gives a diagram that is a mess. No complete the first cycle of charts. It's not representative. And the second put cell it's true that complete the first cycle of chart, but the unload process is immediate, instantaneous. So this result give us information about the stability of the put cell, and maybe the results are false. It's the first time that someone print the electrodes to produce a put cell, so we are proud, and I think it's promising. So, and to finish the presentation, here some conclusion about my experience working in a startup. It's hard, okay, but gives you the possibility to learn a lot. To obtain, give you a 360 knowledge about the company, market, science, human resource. This is important because all study in the university, but to achieve the success of the company, need change a little bit the mindset to a business perception. You have to get out of the box. Risk and uncertainty is normal. I wasn't used to with this kind of concept, but now it's my routine, so welcome. It's very fun. It's true. It's fun. There are always things for, and the most for me, I like it. It's always chilling you. It's passionate, so I'm happy to work in a startup. So thank you for your time.
Thank you for your presentation, Inés. Very interesting. So, do we have questions from the audience?
I would like to know the capacitance of the full battery system.
The put cell.
Yes. The capacitance.
I don't have this diagram, sorry. But I think no would.
But you have shown us the capacitance cycles, I guess, but it was just from the
yeah. Maybe because the result.
I have one question related to, I know very little about 3D printing, but I mean, you sometimes when you do 3D printing, you can use a sort of polymer, right?
Mm-hmm.
And you use light in order to harden it. But you're using ceramics. And then how do you harden? I mean, how is the process going? I mean, do you use powder initially, deposit powder, and then you
No, we use FDA in general, fuse deposition modeling. We introduce a filament, and this filament is based on an organic part that is a thermoblend, a thermoplastic blend. Okay, and then first we mix, okay, the thermoplastic blend with, and we introduce a ceramic powder. We mix, we dry, we make the pellets, we produce the pellets, and then we extrude and make the filament. And then we use this filament to introduce in the 3D printing machine and print the part. We don't have a bed, a slurry bed, or a powder bed. First, we form the chemist formulation. I do the chemist formulation, and I think, okay, this proportion of binder and this proportion of ceramic. and we mix, and then produce the filament.
Thank you.
Have you ever tried this technique in Satan?
If we try,
Yes.
no, but we are working on it.
Why did you decide to go for electrochemical applications for these materials?
For the grant, and because it's a potential target market. It's interesting, but it's hard.
Yeah, of course, but what is the advantages that you expect to have with
The
the
free-
ceramic electrodes?
The freedom to design.
No, with the ceramic electrodes.
No contaminants. Green environment or no contaminant. For example, or yes, for this reason. And lose, reduce the weight.
Yeah, the advantages, yeah, the additive manufacturing is that. And also, did you thermally treated the drop cast electrodes, or just prepare them and use them as a common electrode for the cells?
What? Can you repeat this?
Did you thermally treated the drop cast electrodes
Yes,
also?
yes.
Yeah, because I have the same question, because you say that the difference and the results that you have with the electrodes that you prepare
Yeah,
with the Dr. Blade was
Yeah.
in that case, you have the organic, and in your
Yeah.
case, you don't have the organic. You don't have
because
the organic
remove the-
because you remove the organic, but you can do it also in the ones
Yeah.
that you casted.
yeah,
You didn't do for any specific reason on those?
because if we don't have organic part, the electrochemical properties improve.
But you can do that also on the ones that you casted,
Yeah,
but you didn't.
no.
Because you are not in advantage ones to the others.
I don't understand.
No, I understand.
Okay,
Now we
okay.
can discuss later. Okay. So, I have many questions, but the filaments, I don't know if you can answer because your main, let's say your main business is the material itself and developing the slurry and the composition of that, and that's where where is your expertise.
Mhm.
Okay, so if I'm thinking in a normal 3D printing machine using a polymeric filament
Yeah, for example.
and so on, okay, it's really flexible and so on. So this one, I guess, is also kind of flexible.
It's flexible, como dice las comer
Okay,
our filament.
and can be
and then-
used in any 3D printer of FDM
Yeah,
in a free code also.
yeah, with Pura, for example.
Okay, I'm just
Yeah.
asking. So I'm thinking in having business to business.
Yeah.
So it's possible that you develop a formulation with the kind of materials that we provide you,
Mhm.
and then you prepare the filament for
Yeah.
printing in there.
Mhm.
That's very interesting for us. Thank you.
So in theory, you can use any material, any ceramic material in your formulation.
Yeah. In general,
Did you play with the particle size?
yes.
Yeah, I know. I can understand. And have you any way of controlling the porosity after printing?
Yeah, with the thermal treatment, like we see in the same picture.
Thank you. No questions there? No question?
No.
Yes, thank you for your presentation. I was wondering, you can say, what's the volume of ceramic that you are using with the filament, the maximum that you can use?
Maximum 19, 80,
90%.
yes,
And what about
more or
this?
less. It's a
It's a lot.
It's a lot.
Yeah, it's a lot.
It's a lot.
And what about the shrinkage of your samples after dividing and so on?
we always have a shrinkage for the remove the organic part. We oversize in the first step and
So it's easy to control.
no.
And also, for example, do you consider some kind of, I don't know, multi-layer 3D printing with different ceramic materials to improve the properties? Or for example, directly to print with another material, the battery case of
Mhm.
your ceramic 3D example?
Yeah, it's a possibility, but I'm not trying yet.
Thank you.
No question. Yeah. I think. A question?
No, que no questions.
Okay. I just a curiosity about the, you said you have the 3D techniques, the 3D common techniques for 3D printing, but mainly you use FDM. But the option of the stereolithography,
Mhm.
you also work on that?
Not yet,
Okay,
because our vending is not photogravable,
okay.
but depends on the formulation. Maybe we introduce. I don't know.
Yeah. I don't know if there is in the market people working on stereolithography with ceramics.
Yeah, it's interesting in the market.
Yeah, it's the main market. Technical ceramics. Street one, yeah.
Because the quality is better.
And the resolution that you can.
Yes.
And the most expensive.
Yeah,
Yes.
I know, that's usually. Okay, so we don't have more questions. We thank again the speaker. And close the session. Thank you. Yeah. Yeah.